Hi, I'm Fernando Pereira from UFMG in Brazil, and today we shall talk about unification, which is the algorithm used to solve the constraints that we regenerate through type inference. Unification is a rather simple technique, but with powerful consequences. It determines when two structures, potentially with open variables, are the same. So, an open type variable unifies with itself, or with anything that does not contain it. Two ground types unify if and only if they are the same, and two composite types unify if their subparts unify. Notice that we cannot unify a type variable with another structure that contains it, plus something else. Like in this example in which alpha1 unifies with tau2 arrow alpha1. Unification will try to build an infinitely long type, in this case, an infinitely long sequences of tau2s. I will show how unification works using these constraints as an example. So we start with the red constraint. We have that the two terms at the left of the arrow expression unify. That gives us that alpha2 and tau1 unify. And the terms on the right of the arrow unify too. So alpha1 arrow tau0 and alpha3 unify. Notice how unification creates equivalence classes. So if we have this new constraint in red, now we add tau2 arrow alpha4 into the equivalence class of alpha3. Notice that we keep unifying parts of the types recursively. So we unify the arrow types in the class of alpha3. That creates two new equivalence classes in our system. The third constraint, alpha4 equivalent to tau2, will force the unification of these classes. And then we have a trivial equivalence, which we can drop. And a constraint that forces us to add in int into the class of tau1. Then we also must add int into the class of tau2. Notice that we have two classes with int, thus we can further unify these classes. And that's the resulting system that we obtain. The next constraint does not change it because both alpha4 and tau1 are already in the same equivalence class. And the same holds true for the last two constraints. And with this we are done. We have found two equivalence classes that solve the constraint system. Here we have an implementation of the unification solver. This relation called solve receives a constraint plus a world of equivalence classes called sigma. It then changes this world given the input constraint. You can take a look into the for rules. I suggest you to stop the video and then read all these rules. We assume the existence of a function called unify that implements fast unification. So now that we have solved the constraints, we need to replace type annotations with actual types. We can do this with a renaming system, which assigns names to each one of the equivalence classes that we have. These are the naming rules. Each rule determines how we find a suitable name for an equivalence class Q. This name will be the name of any type that belongs into Q. So if Q contains a ground type without arrows, this type is the name of Q. Otherwise, we do recursion to find the name of each side of the arrow type. Notice that sometimes we might have to generate a new name for some class. That means that we have a polymorphic program that is quantified on some type. For instance, that would be the type of the length function that receives a list of any type and returns an integer. Let's see how we can find names for these equivalence classes. First of all, notice that int belongs into one of the classes, thus the name of this class will be int. And the rule for arrow types let us infer the name for the second equivalence class. Once we have found names for all the equivalence classes, we use a function to rewrite the name of type variables with the names inferred in the previous step. Here you have the renaming rules. Notice that the only rule that effectively changes the name of a type variable is the one that applies on lambda abstractions. In this case, we use the name inferred in the previous step to annotate that function's argument with the correct type. In other words, the RW function takes a program with open type variables like this one on the left and replaces it with a program in which every type annotation is a ground type. Let's see how type inference would work for this example. These are the constraints that we infer for this program. And after unification, these are the equivalence classes that we end up finding out. The naming procedure would give us these names. Notice that I've sorted these equivalence classes in terms of dependencies, meaning that if I have an arrow from one class to another, that's because the destination depends on the origin. Has some variable like alpha5, for instance, that depends on the origin. And the RW procedure would give us this final program where type variables have been replaced with the ground types in red. Notice that this is a polymorphic program, meaning that the type T, which is quantified with the for all symbol, can assume any possible concrete type. And this last example closes our class on type inference. Notice that most of the notation used in this class has been taken from Mellow's paper, Inference of Static Semantics for Incomplete C Programs. This paper describes a type inference engine for C. Thank you.